Hello everyone. So we have been discussing about shock wave attenuation, interaction and reflection. So what we discussed in the last lecture is that the impact of a projectile of thickness d naught on a semi-infinite target. So and we have shown that time and distance plot, and then now we have shown the pressure distance profiles as well. So now we will continue this discussion, and so we know that the Rankine-Hugenoid curve for an ideal hydrodynamic case, that is ideal hydrodynamic material. So we will draw that. This is a plot of stress sigma x and the strain epsilon x, which is the shock wave is going in this direction, and the x direction, shock propagation direction is x direction, in x direction. That's why we're using sigma x and epsilon x. This is basically what we did is we are replacing the pressure P with sigma x, and we are substituting epsilon x for 1 minus volume, the current volume divided by this initial volume. So this is basically the Rankine-Hugenoid curve. Hugenoid curve for an ideal hydrodynamic material. So where this is, I can write ideal hydrodynamic material. Okay. So this means basically that hydrostatic stress at shock front. So that means sigma x, sigma y, sigma z, which is equal to minus P. So only hydrostatic stress exists here. We will see how first we get this epsilon x equal to 1 minus V by V naught. So what happens, we are assuming only the shock propagation in the x direction. Let us say we have a volume here, something like this. So this in the x direction, the shock wave propagation direction. So we have, let us say, the size of this element, we have L naught, L naught and L naught. So after the shock wave will propagate this, it will compress the material to something like this. Now, so in this case, as we know, for shock wave along x direction, what we can assume is strain in the y direction and strain in the z direction will equal to 0, because shock wave doesn't allow lateral strain. Assumed to be, the lateral strains are assumed to be 0, and that means it's a uniaxial strain case that we already discussed, that shock wave is a uniaxial strain case. So this is the assumption, uniaxial strain. And so now coming to this, so if it is the shock wave direction in this direction, so this will be compressed to L. Now the current, this L naught compressed, this L naught will be now L, but the other two direction there is no lateral strain, the other two direction L naught will remain same. So what we can do from this, we can calculate this epsilon x, which is equal to L naught minus L divided by L naught, and then if we multiply this with the area, this L naught square, let's say we took L naught square by L naught square here, and that will give you V naught minus V, the volume, divided by V naught, and which is nothing but this one. So this is the same. So now what we talked about, this again coming to this diagram, this the plot of Rankine-Hugenoid curve. So non-hydrodynamic component of stress can come into picture when that HEL, that Hugenoid elastic limit, is not negligible. When HEL is not negligible. And that means HEL is not negligible, that means that elastic deformation precedes plastic deformation and as you know, this plastic deformation happens when the shear stress tau is equal to tau yd, that means dynamic yield shear stress, dynamic yield, that is shear stress, not their normal stress, the dynamic yield shear stress. Coming to this pressure to sigma x conversion, so what we know that the pressure is that hydrostatic component can be we can find out as this one, so that we already know, and that means this is initial strain case along the shock wave direction is along x, so sigma y and sigma z will be equal to and that will give us sigma, or we can write this twice of sigma y, and that will give us 1/3 of thrice sigma x minus twice sigma x. So we are just trying to get one expression, which is, you will see from here now. So this is equal to sigma x minus 2/3 sigma x minus sigma y, and which we can write as sigma x minus 4/3 tau max. That you know that maximum shear stress tau max, I will write in above, tau max is equal to half of sigma x minus sigma y. So we wrote it here, and that tau max is in this case nothing but this tau yd. This tau max is the tau yd here, so that means P, we can write it, although it's very messed up now, so but I will write it here, P equal to sigma x minus 4/3 tau yd, and the other way what we can write is, we can write the other way, and then we can write it as sigma x is equal to P plus this. Earlier we wrote P equal to sigma x plus this, so this is the relation. So from here what we can do is, we need to as you can understand that if HEL is not negligible, non-hydrodynamic component of stress, that not only the hydrostatic component, the other component of stress are also need to be accounted for, and in that case, so so we have the HEL we need to be shown here in this plot. So HEL is, this is corresponding to HEL, and then we'll have a parallel curve like this. So after elastic deformation we have a plastic deformation, and if you measure this, that you understood that this is, if the pressure, and that will be equal to our 4/3 tau yd, and if you want to draw the unloading curve, it will look something like this. The unloading curve will come here, and there will be a parallel line, parallel curve, which will come like this. So this doesn't look parallel, or otherwise we need to make this curve little better here. Okay. Yes. So now this is the Rankine-Hugenoid curve. The first curve was the Rankine-Hugenoid curve for ideal hydrodynamic material, but if we consider the that HEL is not negligible and non-hydrodynamic component of stress, then the actual real curve will look like this. And if you do unloading, this is unloading, and this curve will come and goes like, return backs like this, and this portion is the hatch area. Actually this shows the irreversibility of this process, irreversibility of the process. That means that curve doesn't come back in the same way, so it has a reversibility, and that is because of the elastoplastic effect. So you have elastic deformation and then plastic deformation, and that contributes to the rapid decay of the shock wave, because the shock wave will dissipate energy because of this irreversibility. And this is also called the unloading. We call this is hysteresis effect. Hysteresis effect. So this and this distance, as I told, this is 4/3 tau yd, and the entire distance will be actually 8/3 tau yd, the dynamic shear yield stress. What we discussed about is that the Rankine-Hugenoid curve may not be always look what it look like for ideal hydrodynamic material. So it if you consider the Hugenoid elastic limit, that curve will can give us the irreversibility that is due to elastoplastic deformation. Let us discuss about the attenuation of the shock wave, so that we didn't discuss much earlier. So what is attenuation? Attenuation of the pressure pulse. So that attenuation means the decay of the pressure pulse. As it travels through the material or the target. Through the material. So what happens, even we discussed earlier, so we will draw this. We have pressure versus distance. Distance means the distance into the target plate, or the projectile will hit the target, and so we are measuring this distance into the target. Suppose from the left hand side the projectile hits, and we will see the pressure pulses here into the target and this, suppose if x equal to 0, you can assume at that point x equal to 0 is the impact interface. So initially the shock pulse will look like this. So this is the maximum pressure, the peak pressure. I can write Pm as a peak pressure. So the shock wave velocity us1, let us say at this position that shock wave velocity us1, then after some time this, as we know that that is the shock front, the right hand, this line is we call the shock front. Here also the shock front will be the same, maintaining the same peak pressure, that is the peak pressure Pm. So we have, let us assume the velocity is us2, which is nothing but the same as us1 now, and then this behind portion will not be a straight vertical line, it will be inclined line. It will be straight line, but it will be inclined line. This is, as you know, this comes from the interaction of the this release wave. Release wave means the reflected wave that comes back from the back surface of the projectile. So this is the release wave portion. So we can have this velocity of the release wave, which is, we earlier had that c plus up. C plus up. C is the sound wave velocity at a particular pressure P, and up is the particle velocity. However, after some time what will happen is that this plateau or the flat top will disappear, and then the pulse will look like this after some time, after some distance it will look like this. And then pressure, the peak pressure will decrease. The peak pressure earlier was here, and then it will decrease. And also if you see the back side this curve, that is the release part where the pressure returns back to 0 value, from the peak pressure to the 0 value, that also have a now the slope is less now. Earlier the slope was high, in this point the slope was high, here now slope is less. And then let us say this is us3, the shock wave velocity, which is lower than us2, okay, lower than us2. Again if we draw it here one more step ahead, some distance ahead, so it would look like this. So this will be, pressure will be again reduced, and let us say the shock wave velocity us4, which is even lower than us3. So now what is happening here, so we shall see this, what is happening here. So the release, as the wave progresses, the release wave overtakes the shock wave. So you have this shock wave, and this we have the release wave. So what happened, the release wave is also travelling in this direction, and the shock wave is also travelling in this direction. The velocity here is us, or different times we are writing us1, us2 like that. And then the other case, the release wave, which is reflected back from the back surface of the projectile. So it has almost a constant value, and this c plus up is higher than the us. So that is why the release wave will overtake at some point of time, overtake the shock wave. So here if you see the in the suppose this is case 1, case 2, case 3, case 4. So in case 2 still the release wave is behind the shock wave, and but in case 3 what happened is that released wave already overtook the shock wave, and that is why this peak pressure that was earlier PM, now it is got reduced, and similarly for the number 4 case also it even reduced much to a lower value. This duration of the pulse, we call this is the duration of the pulse, that is we can write it as xp, which is nothing but the time duration is Tp multiplied by us, or in this case us1 will give the pulse duration, and the distance the pulse travels. This will be reduced as it travels, the shock wave travels through the material, and then when the release wave overtakes the shock wave, that pulse duration will be 0, and then after that it will the pressure will be reduced. So after pulse, I will write it here, after pulse duration becomes 0, pulse duration is nothing but the Tp becomes 0, the pressure starts to reduce. The peak pressure. Also you can see if the peak pressure got reduced, if P decreases, the peak pressure decreases, US also decreases. That is we have not discussed this much, but it happens. If you can see these experimental values also, this with the pressure that shock wave velocity decreases. So that's why you can see that US2 and US1 are equal because the peak pressure is same, but US3 is less than US2 and US4 is less than US3, that you can see from this plot. And by appropriate computational techniques, now we can calculate the pulse shape. We can calculate pulse shape. So by computational techniques we can calculate the pulse shape based on the velocities of shock wave and the velocities of release wave. The rate of release also very much dependent on pressure P, and that is why even impact velocity and the fly plate velocity can change the release rate. So I will write it here. So pressure P can change. If the pressure is changed, then rate of release, that rate of release, as you know, the release means from the peak pressure, or if you can see in this, from the peak pressure the pressure returns to 0 pressure, that the rate of release depends on the pressure. And also if it depends on the pressure, then also Vp, that the impact velocity of the projectile, and also the thickness of the projectile, that is d naught, that can also change the rate of the release. So the rate of release depends on these factors. And attenuation rate, if we talk about attenuation rate, that is the rate at which the pressure pulse dissipates itself as it travels through the material. So that is the decay rate of the pressure, and then energy carried by the pressure pulse is dissipated as the pressure, as you can see from the earlier plot, the pressure will decrease, and that means the energy dissipated, that can be converted as is heat or defect structures. Defect structure means and also there may be some other processes. Defect structure means, for example, dislocation structure. Dislocation is a crystal defect, dislocations or other defects. The attenuation is decided by the relative velocities of shock wave and the shock wave and the release wave, the velocities of. So, the relative velocities of shock wave US and release wave C plus UP determines the attenuation and the attenuation rate. So, the distance till what point the peak pressure will be maintained, that can be calculated with some simple calculations. So, that distance we write it as a S. That distance can be, I am just writing the expression, no derivation. So, this will be UP plus C minus US. You know all terms, I even discussed about TP as well. So, this is the distance that peak pressure is maintained, distance into the target material. So, distance up to which peak pressure is maintained. Peak pressure is maintained, and as you know, after this distance the peak pressure will fall down, and then beyond this point numerical beyond this point, beyond that distance, numerical techniques can be used. Can be used to compute that pressure decay. So, this predictions of pressure pulse so the prediction of pressure pulse using hydrodynamic theory is not very realistic. Prediction of the pressure pulse decay, actually the attenuation, prediction of attenuation of pressure using hydrodynamic theory is not realistic, So, actual attenuation rate is considerably higher, real attenuation rate is considerably higher. There is one work by Erkman sorry, it's an old work by Erkman and other workers, researchers. It's published in 1966. He showed that if we plot particle velocity UP versus target thickness by plate thickness, let us say T by, which is, we can write the ratio R, T target by T target thickness by projectile thickness, and that the flyer plate thickness. So, what happens is, if we use the hydrodynamic theory, we can see that the peak pressure will maintain till a long distance. That means, if it is around 16, the target thickness by the plate, the projectile thickness, and then it will decay down, it will decay like this. But for experimental cases, it looks something like this, and even these are some experiments did earlier, but now some sophisticated codes can be used which can give relatively better results, a much better result actually. So, this goes some codes shown in this textbook. So, this goes like this. So, basically this is the experimental that I want to show you. This is the experimental one, and this is the using this curve shows the hydrodynamic theory. So, if you can see the pressure drop here for the experimental curve is the rate of attenuation is considerably higher. This experiment was done with aluminum target and aluminum projectile. Both are same, the projectile and target are aluminum, and so there are the advanced codes like what I showed you, this curve. So, these are based on some advanced models, which is, let us say some models with elastoplastic model with some artificial viscosity term. So, we are not going to discuss about these models with artificial viscosity consideration. Just to let you know that there are some advanced mathematical models that can predict these experiments very accurately, at least much accurately than the hydrodynamic theory, which is, you can see, is very different from the experimental findings. One more publication, Shu and his co-workers did in 1981. So, this group actually did a plate impact experiment to study the metallurgical aspect, that is they did it on nickel, study the effect of metallurgical aspects. Metallurgical aspects on attenuation. So, and what are these metallurgical aspects? This is basically grain size and dislocation structures. So, we will discuss these things a little bit later, but I hope that you all know about what is grain and what is dislocations. This is basic material science, all of you have studied. So, effect of grain size and dislocation structure. Dislocation structure, it may mean even the density and distribution of dislocations. Dislocation is the primary cause of the plastic deformation. Dislocation is nothing but a crystal defect. So, and they found out that there are no effects actually, no effects were found from their experiments, and they measured the peak pressure. They measured peak pressure two places, peak number one is close to the impact interface, that is in the target impact interface, and they measured at a distance 10 centimeter from the impact interface, that means into the target. So, what they found is, so they found that even I will roughly draw a plot of pressure versus distance. Sorry, this is x. So, as you know, the pressure pulse will first it will look like this, then the pressure pulse, the back line will be little inclined, and then this will be look like this, then pressure will decrease something like this, something like this. So, now what they did, one point, the experiments they did, one point they took the very close to the surface, this is the impact interface is x equal to 0, very close to the surface they took, and then pressure point they found it somewhere here. So, close to the interface, they have they got good results, that means the predictions were good, the predictions are close, but at a distance of 10 centimeter, at the distance of 10 centimeter, let us say this is the 10 centimeter point. So, here the pressure they got it something like this, so which is much lower than the peak pressure. But if you see the if you use the hydrodynamic theory, sorry, I actually probably forgot to tell you this, whatever plots we have, this is from using hydrodynamic theory, and they had two experiments. I mean, they have one experiment with two positions of measurement. So, the second point is here at 10 centimeter from the surface, and here you can see that predictions are much higher. So, that means the peak pressure prediction is higher. So, the theory says it will be in this point, this place, that means the attenuation is higher in real case. So, attenuation is higher in real case, in the previous slides we discussed about it, and with hydrodynamic theory the attenuation is lower, attenuation rate is lower. With if you do a real experiment, attenuation you will find it as quite high. So, we will close this today's lecture. So, what we learnt here is about, we are discussing about attenuation of shock waves. So, what we will be even continuing with interaction and reflection of shock wave. We will see how the shock waves interact when it transmits from one material to the other material, and when it reflects back from a free surface, or when two waves superimpose each other. So, this discussion we are keeping it for the next lecture. Thank you.